As you can see, we had a first session from my side on quantum, sorry, not on quantum, classical mechanics plus quantum mechanics, which is Lagrangian mechanics and Hamiltonian mechanics. Okay, Lagrangian equation and Hamilton's equation. Those things we discussed. Okay, so as you want me to connect to my previous the lecture. Okay, so what did I do? I did Lagrangian mechanics, Lagrangian formalism. Okay, basically this is, let's say there are cases where Newtonian laws could not be applied. In the sense they may be applied but complicated. Okay, in that case, Lagrangian formalism is very, very handy. So that is where we just a minute, let me reduce the thickness slightly. Okay, I discussed that. And then it is applicable to classical scenarios. Okay, this is for classical scenario. Okay, but when I go for quantum scenario, in the sense quantum scenario means very small level, at quantum level, Lagrangian formalism doesn't work. We have to use Hamilton's or Hamiltonian formalism. Okay, we discussed those things. So keep that aside and we will see wherever is required. We'll try to connect that for today's session. Okay, so before getting there, quantum sensing, first of all, we should understand what is sensing. So, what is sensing? Okay, what is it? And if that is a sensing is we understood, are we applying sensing at what level? We just saw sensing could be applied, any dynamics could be understood at a classical level or a macroscopic level, and dynamics could be understood at quantum level. Okay, so same story here. Sensing could be applied at a classical level, or you can say macroscopic level. Okay, and also quantum level. Okay, what I mean is at a microscopic level, to sensing at microscopic level. Okay, so we'll just try to understand what is sensing and we'll get into the quantum level microscopic sensing. Okay, that is what we want to know in the first place. We will no need to go in detail what is a classical sensing or the sensing at the classical level. We'll not get into that. We'll just get the idea. Okay, so let me take a simple example where you will be able to understand what is that is. Suppose I have a large charge. Let's say I have a large charge. Okay, the positive charge is there. So the nature of the positive charge, let me draw that little bit down. Okay, let's say I have a large charge Q. The nature of that positive charge is it emits electric field lines. Okay, this is the nature of the charge. Okay, means it is sending its strength outwards. Okay, so what it is doing is, if at all, okay, what it is conveying to its surrounding is, if at all, if there is any negative charge around, then it will be attracted. As you guys know, opposite charges attract. Okay, but why do I show the arrow pointing outward? The arrow pointing outward, what it is conveying is, If there is any positive charge around, okay, that charge, then that charge will be repelled away. That is the arrow mark actually pointing out. As you know, we will say people, we got intimidated by somebody. Okay, right? We say intimidated by somebody because he is more knowledgeable. He is very heavy. Like, say people will say, oh, he's a big guy, so we'll not go near to him. Right? That's what this positive charge is large. So he sends charge around, sorry, fields around, his strength around, his electric field around. Basically, he is creating electric field strength, which is simply equal to 1 by 4 pi epsilon naught q by r square. Okay, so the direction is outwards from the center, r cap. So this is what he is sending. Now, whether this guy is present there or not, how should I know? Right? Somebody was asking a question here. Let me see quickly. Okay, what I think he asked, what is the origin of the charge here? Okay, it's a good question. So when I say charge is there, how did it come? And is somebody brought in or somebody picked up and put it here? Okay, so let's say I have knocked an atom from, let's say, a collection of some atoms from some material. I put it at this point, and for that material, what I do, I knock out some electrons from each of the atom. So what happens, each atom becomes a positive positive charged ion. So all those positive charged ions, let's say, they create a positive charge q. Okay, that is what I was showing here. Large q means some charge, positive charge distribution at that point. Now the question is, question, how to how to recognize, okay, how to recognize this positive charge. Okay, how to recognize this positive charge. Okay, so the answer is, we can simply bring another small test charge q. Okay, small q. So what I'll do, I'll just bring small test charge q. Okay, you can take small test charge either positive or a negative. So usually people take a test charge small q. Now what happens, on this small test charge there is a force created. Okay, so a force is exerted on test charge. What is that? Is simply q multiplied by e. So which is in fact equal to 1 by 4 pi epsilon naught q into q. R square is the distance between, r is the distance between the test charge and the source charge. This is simple electrostatics for you. Electrostatic force, you can even say electrostatic force. Here nothing is moving, test charge is not moving, and source charge is not moving. Small q, capital Q, both are not moving. Even small q has its own electric field strength going out. Okay, but the thing is, the test charge is so small that guy feels some force sending away. So how, with what force he is going away, that would dictate what is the strength of the actual source. Okay, so here if you see, a sensing is done by using another small charge. Okay, so what I would like you people to gather the information here is, let's say I want to find or recognize something of a, let's say, a positive charge. I use another kind of a charge, another very small tiny charge, which gets which actually going to experience the force, or which going to experience the presence of that large Q, uh, we is used to recognize that. Okay, so this is a sensing. This is some kind of a sensing, right? I hope you remember now what is. Okay, I hope you recognize what is the sensing here. Okay, similarly, right? Similarly, okay, what even you can do is similarly. Let's say I want to sense a large magnetic field, right? Another example, okay, a large magnetic field, right? What is the largest magnetic field? Earth magnetic field. Earth, Earth magnetic field, right? Earth, south, north and south pole are actually pointing very close to geographical north and south, but slightly tilted. So what people use, the like for example, sailors on the ship. Even now also, the captain of the ship still carries a very small compass. Sailors use a magnetic compass, okay, to sense the large the large magnetic field, okay, of Earth's magnet. Okay, see here again a very large, see for example Earth magnetic field is there like this, north and south. The magnetic field lines goes from north to south. Okay, remember this is how there is. If I want to know in which direction the north and south magnetic fields are going, or in a way, in which direction in the ocean I am traveling, am I traveling in the direction of north, geographical north, or south, or east, or west? So they use a small compass, very small compass. Compass is nothing but there is a small bar magnet, north and south pole. Okay, right? So what this compass does is it aligns as per the external magnetic field. Now you see this also has got its field lines. Okay, so but the problem is they're actually just in the same fashion as the external magnetic field. Let's say when we bring together, what happens? It exactly aligns opposite. Yeah. Okay. South north. That is how the magnetic field lines actually. Okay. Sorry. Yeah. Right. So alignment takes place. Alignment as per external magnetic field. Okay. Brings to when you bring together. Okay. Right here, you see the strength when you bring together, the alignment takes place. When the alignment happens, they get attracted because, see, in a way, they are arranged in opposite way. They get attracted. So, with what strength it is attracted, you will know what is the strength of the external magnetic field. Okay. So, depending on the alignment, the magnetic field strength could be recognized. Okay, so depending on when you try to bring two magnets together, they attract. So with the opposite polar manner, if you arrange, they attract. And what I mean is, if you try to bring north north together, so they repel each other. Okay, it's very difficult to bring them together. Otherwise, on the other hand, if you bring them opposite, south north, they attract each other. They attract. Okay. So depending on this, you can find what is the sensitivity of external magnetic field. Okay. So these are the simple basic scenarios which we would be using to sense electric field and magnetic field. So what is the take home here is, okay, to sense of a field, or let's say a field or a signal. If you see, we use another means which is having of same nature. Okay, see what I mean is, to sense electric field, a small test charge I use. To sense magnetic field, a small bar magnet I use. Okay, so that is the take home. The same way, if some patient is sick, let's say a thermometer is not there, what person, like a doctor does, holds its hand and sees the temperature, holds his pulse. Okay, try to find his pulse. Or if there is a thermometer is available, what people do, they will put thermometer either if in the mouth, or they just use depending on what kind of a thermometer is. Based on that, what happens? Thermometer, it has a mercury inside. The mercury expands depending on how much expanding happening. In that way, they calibrate how much temperature the person is having. So the idea is, the heat itself is used to recognize what temperature the person is having. Okay, so this is the motivation here. So sensing, the idea of sensing could be based on the actual signal itself. If it is an electric field, I use a small electric charge to sense that. If it is a very heavy magnetic field, I use a small magnetic compass to measure that magnetic field. Okay, so this is a classical, like a macroscopic level, the sensing is happening. Okay, right? So magnetic sensing is happening at a macroscopic level. Now, what I will do, we will try to use that idea to our quantum computing. So, our quantum hardware. We are into the quantum computing or quantum hardware, where we will be using the quantum qubits. Okay, right? So why do I am talking about quantum qubits? Because we will actually process the information through quantum qubits only. Okay, so we need to know how these quantum qubits are undergoing some change. Okay, if there is large number of qubits are there, how these qubits are going to influence the other qubit nearby. Okay, right? So let's say there is a large electric field is there, how is this electric field is going to influence the qubits? Okay, so in the quantum sensing, one should understand, okay, one should understand how the given information carrier, okay, right, information carrier, okay, carrier like qubit, okay, how this qubit gets influenced by external fields. I will just say external fields or signals. Okay, so there is something around that is going to influence some change on the qubit. Now, how much change in the qubit I want to sense? That is one way of sensing. Okay, so one way that sensing can be in a multiple ways. It can happen. Sensing can happen in multiple ways. Now, okay, let me give those things. Number one is how the given qubit gets influenced. Okay, that's one question. Or number two, how this qubit is going to influence its surroundings. Okay, so there are two questions, two sensing questions you can ask here. One is, let's say there is a qubit which carries some information, how it is going to influence the surrounding, or how it is going to be influenced by its surrounding. So those two things I should know. So to know that, I need to sense something. I need to see how much change it has, it underwent, or how much change it actually induced to the surroundings. Okay, right? So now, to understand, let's put the qubit in a mathematical form on paper. That is easy, right? We don't have experimental equipment to see how a qubit undergoes some change. So what is the best way is, I just take a qubit in the form of mathematics. Okay, so let's consider qubit in a mathematical, okay, expression. Okay, that's easy. I can just influence that. So what I do, I just write a quantum state in a Dirac notation. Quantum state psi is equal to alpha 0 plus beta 1. You guys know this form, okay? Where alpha stands for the quantum qubit to exist in 0 state, and beta stands for the probability amplitude with which, okay, the with which the electron or an atom, if you choose, if it exists in two levels, okay, right? So it can exist either here or here, okay, okay, right? Just a give me a minute. Okay, right? So electron can exist in the ground or excited, okay? So if actually what it is doing, it is actually hopping between ground and excited. It is staying between 0 and 1, sorry, staying in 0 also 1. That is what represented by alpha 0 plus beta 1. Now, let's say it is ideal, it is not surrounded by anything, it is just inside a box which is vacuum, the temperature is very much fixed. So, literally, it is not going any change. Let's say ideal situation. In that case, this holds good. Okay, completely, I would say completely, okay, completely, what should they separated, or so completely ideal situation, okay, ideal scenario, right? You are able to separate the electrons or atom completely away from the environment. Now the question is, let's say the environment comes into play. What I mean is, let's say even if you take so much care, you cannot influence, like you cannot like confine this qubit to not to interact with the surrounding, because it is so much fragile. Because of that, what happens? The quantum state is going to change in time. Why? The probability amplitudes are also going to change as per the time. So here I'll write the probability amplitudes are actually the functions of the time. So the moment they become a functions of the time, the quantum overall state also becomes a functions of the time. Okay. So what I mean is, let's say at some point t naught, a quantum state is there. T naught, a quantum state is there, which undergoes a change, or I can say undergoes evolution to what? A quantum state later on, let me say a T1 time. Okay, right? Some evolution it is undergone. What is that evolution could be? It could be, let's say, if you interact with the surrounding, it might lose some information to the surrounding, or it may acquire some information or some energy from the surrounding. All those things are possible. So mathematically, the evolution, I would write it as some kind of a transformation of T1, okay, some transformation of quantum state at T1, sorry, T naught to T1 with some transformation matrix. Okay, here I will write the transformation matrix. Okay, here I'll write the transformation matrix as some unitary matrix you already know by now. The unitary matrix would describe the change of quantum system from some t naught time to t1. That is what I have written, a transformation matrix. Okay, so the unitary matrix is such a thing which would explain or describe how the system is going through some change. Okay, so that means the key is in the unitary matrix for us to do some sensing. Okay, so remember, unitary matrix would help me. Unitary matrix would help us to understand the sensing. Okay, right? So if at all, if I have to sense that field, or if I have to sense the effect of the surrounding on the qubit, again, this U is having to play a role. Okay, right? So now, as you guys already know, the unitary operator or unitary matrix here is a unitary gate. Okay, so in fact, this unitary matrix captures the information of, okay, so U actually captures the information of the system, okay, plus surrounding. That is very important. Okay, it captures that information. So the question is, what is the form? What is its form? What is its form? You can ask that question. Let's say I take a qubit. What is a unitary operator which describes the quantum qubit is going to undergo some change? Okay, right? So just we have understood, like we discussed in my session earlier, unitary matrix is going to have a Hamiltonian of the system. Hamiltonian, okay, Hamiltonian, okay, would be used to construct a, unitary operator. Okay, right? So what I'll say, the surrounding would decide what would be the change can go on the system. For example, even it is suited in real world. For a classical world, in a classical world, if you just take example, okay, a glass of hot water. Okay, if you just take a glass of hot water, okay, so there is a hot water, you know how much time it will take during the winter to cool down. Okay, how much time it will take during the summer to cool down. So around surrounding temperature, surrounding humidity, all those things would be matter. Okay, the surrounding, I'm in a class, the surrounding would decide how much time to take cooling down, for cooling. Okay, so that means the surrounding has a say in deciding the fate of the qubit, means we should worry about that. Okay, so in fact, right, yeah, in fact, one minute, yeah, so in fact what we will do is, we will just try to write the Hamiltonian into the unitary operator. It can't simply write. So what we will do, we'll just say, what is the Hamiltonian? Hamiltonian is what? It is going to say the total energy of the system. Hamiltonian is total energy of the system. Okay, as we know. For example, here in this case, the Hamiltonian is actually written in the matrix form. When I write everything, a quantum state in a matrix form or a column form, if I write, so even Hamiltonian also written in a matrix form. What is that form? It would be, for example, in a qubit case, Hamiltonian would be simply, if I am writing only Hamiltonian of the system or a qubit, I'll write what is the energy with respect to which system could exist in the ground state, 0, and what is the energy with which system can exist in the excited state, 1. Okay, what is this is? It is actually a ground state energy and excited energy. Okay, so literally I'm saying electron either could exist in 0 or 1. If it can exist in both the superposition states 0 and 1, so in that case I'll have a off diagonal terms also non-zero. So they're actually called polarization terms. The moment there is a polarization means the electron does the hopping between 0 and 1. In that case, Hamiltonian will have even the non-zero terms, zero terms also becomes non-zero here. Okay, now Hamiltonian is there. Now for this kind of a system, okay, how do I know the system, like a given qubit exists in 0 state or a given state exists in 1 state? How do I know? For that, what people do is, mathematicians, they take eigenvalue equation, okay, to know more about the system. Okay, what we'll do, we could solve eigenvalue equation. Okay, what is that eigenvalue equation? As you know, if there is a matrix, it is going to have eigenvector which is equal to eigenvalue multiplied by eigenvector. Okay, this is a matrix, this is eigenvector, this is eigenvalue, again eigenvector. Okay, what I mean is, you take a matrix, multiply into its eigenvector, it is equivalent to having, okay, multiply the eigenvector by corresponding eigenvalue. On the left hand side, I have a matrix multiplication. On the right hand side, I have just a scaling of the eigenvector. That is what the eigenvalue equation for any given matrix. So here I have a Hamiltonian matrix. What would be the eigenvalue equation here? Which is H acting on the quantum state, which could be any form, either zero form, ground state, or excited, is equal to quantum state psi. Okay, remember here, I'm in a class, online class. So Hamiltonian and E, here you see energy, both are actually in the operator form. Remember, they're the operator form. Okay, so the moment I use a hat means they're in the operator form. So these things would happen in quantum physics or quantum mechanics. Okay, what I mean is, right? Okay, what I mean is, 5 o'clock after. Okay, so what I mean is, like the moment a variable, if I take variable at a quantum level, it's not a simple variable, it becomes some kind of a probe or an like operator. What I mean is, at, okay, at quantum level, okay, suppose if I want to specify a position of an particle or something, usually we give the position. How do I know the position? I use some probe which measures the position. So in quantum physics, if I want to find a position, I would be needing a position probe. Okay, so it's a position operator. Okay, so what it does, it go and acts on or operate on something. Very important to know that. Okay, so X becomes some kind of operator. So best example which is an operator is P operator, which is momentum operator. Momentum operator. So what I mean is, so in classical physics and real world, if I want to specify a moving object, I specify with the velocity. if I multiply the velocity with the mass of the particle, mass of the particle entity, it becomes P is linear momentum, m into velocity. Okay, linear momentum. So if I want to specify a more linear momentum of some object which is moving, I just specify its mass multiplied by mass with the velocity. I'll get a linear momentum. Okay. But when I want to specify at a quantum level a moving particle, for example, electron, which is a moving particle. Okay. So the moving particle always moves with some velocity. It has some mass. So here I can't just simply give mass and velocity. I need a probe which finds the mass and velocity. That probe is momentum operator. Okay. So interestingly, it takes an operational form which is written as minus IH cross dou by dou x if I want to specify linear momentum along the x. Okay. If I want to specify overall three-dimensional momentum, which would be minus IH cross gradient. Okay, right? Sorry. So this is the operator form. Similarly, if I have a energy of an operator, energy operator. Okay, energy operator is there. So it takes energy operator form as E h cross dou by dou t, or you can say instead of dou by dou t partial derivative. Hello, ಸಾಗರ್ ಆಗಲ್ಲ ಕ್ಲಾಸ್ 5 ಗಂಟೆವರೆಗೂ ಇದೆ. ಇಲ್ಲ. Okay. So what I will say, d by dt derivative. Okay. So the momentum operator is some operational form. The energy operator is in some operator form. So that is what the quantum systems would become in the label or in the operator form. So why they are becoming operator? You can understand. Actually, I have given as a additional notes in my first lecture, which I given. In fact, you can just start from a quantum state in a classical form as some kind of a sine wave function. Okay, kx plus omega t. Okay, now what you do is take, okay, use this and take the derivative with respect to space. Let's say you take a derivative with space, or let's say I want to take a derivative with time. So d psi of x by dt, which is equal to sine. Okay, derivative of sine is a cos. Let me remove this. Okay, cos. Okay, kx plus omega t, derivative of the phase term, I'll get omega. So which is equal to omega psi of x. Okay, what you see is derivative of time is equivalent to just multiplying by omega. So by the way, omega is what? Is an angular frequency. Okay, so usually if I just take h multiplied by mu is energy of the photon. You multiply and divide it by 2 pi. What you get? H cross, h by 2 pi is h cross, 2 pi mu is omega, e omega. Sorry, h into omega is energy. So omega is e by h cross. Okay. Now let me put that in place of omega. Let's put e by h. Okay, right? So now, so instead of, as you can see, sine and cosine, usually the wave function is taken in terms of exponential function. So in our case, which is required, let me take exponential I. Okay, exponential I kx minus omega t. Okay, so in this case I'll get I omega, also I omega I'll get. So d by dt is just equal to I omega. So omega, if I replace by e by h, I'll have I. Now E is equivalent to h by I d by dt, which is equivalent to, okay, I have missed something here. 1 minute. Okay, exponential. Yeah, right. Yeah. Okay. For example, let me take a case of positives going wave. Okay. So for the convenience, I'm taking just for deriving. Okay. So in that case, I'll have a minus sign, minus sign, minus sign. Okay. Which implies is equal to IH cross d by dt. So you got energy, multiplying with energy is nothing but acting with a derivative and multiply by IH cross. So that's why I put a hat form. Okay, right? So that is what you should remember. So the variables in quantum physics at a quantum level becomes an operator. Now let's get back here. We have Hamiltonian and there is a energy is replaced by operator form. Okay, so what I'll do, I just replace in the operator form and I can integrate the entire differential equation becomes a differential equation, right? Okay, I can do that. Or I can also do one more thing is simply bring in, okay, what I have IH cross dou by dou t. I'll write in a partial equation form. It's easy. I have a time derivative is equal to Hamiltonian quantum state. This is what I have. Okay. So in place of E, I replaced with the operator form. Okay. Now, as I know what is the quantum state explicit form. What is that quantum state explicit form is dou by dou t at a given time. It is having some alpha t, some beta t, which is equal to Hamiltonian again alpha. Okay, Hamiltonian alpha t beta t. Okay, right? Now as you can see, so there is a derivative on the left. Okay, I'll have IH cross dou by dou t alpha t is equal to Hamiltonian alpha t. Similarly, IH cross dou by dou t beta of t Hamiltonian H alpha of t. Right? Okay, so here what I can do, I can rearrange. Okay, I can rearrange, send this derivative time to the right. Okay, and to the right, and then integrate. Okay, if I do that, what I will have, I'll have dou by dou alpha t divided by alpha t is equivalent to, okay, minus, right, minus, okay, uh, alpha t dt, okay, so divided by IH cross. So sorry, minus will come when I goes to the top. Okay, so let me put minus on the top. Okay, minus I by H cross dou t. Okay, so now corresponding to alpha t, right? So basically what I have here is H acting on alpha t beta t means literally, I'm sorry, what I'll have is E0, E1, okay, quantum state alpha t beta t. Okay, now what is the first term? First term is E naught alpha t. Okay, E naught alpha t, right? What is the second term? E1 beta t. So I'll have derivative with the beta of t. Beta of t is minus b, okay, minus E1 beta of t dt divided by h cross. Okay. Now, if you integrate on the left and right, what it will give you is it becomes log of alpha t is equal to minus ih cross x e naught alpha of t integration dt. Okay, right? So this is what you will have. Sorry, sir. No alpha t here. Integration of t. So integration of dt is simply t. Okay, this is just minus e t by h cross. So you send the log to the right. So it becomes, okay, first you have to substitute 0 to time t. Okay, so some time t. So I'll have alpha t minus alpha 0, which is equal to minus e naught t by h cross. Okay, so in the case of logs, I can log a minus b means log a by b. Okay, this is what I have, minus a epsilon t by h cross. So alpha of t is in fact exponential of minus e naught t by h cross into alpha of 0. Okay, similarly you can derive beta of t is equal to exponential minus e1 t divided by h cross beta of 0. Okay, so basically what you see here is alpha of t beta of t is equal to a transformation matrix of exponential minus I e naught t by h cross 0 exponential minus e1 t by h cross alpha 0 beta 0. So this is what you have. This is the transformation matrix. Okay, so the transformation matrix here, if you carefully see, which is a unitary operator, which is having exponential minus h, okay, t by h cross. You see, so it's a diagonal. I can just simply use them to get what is my unitary operator. Okay, right? So unitary operator by nature is equal to multiplied by unitary operator dagger, it will give you identity. That is what the dagger of unitary operator is a inverse of itself. Okay, fine. Now that we know, okay, so knowing that, we can find what is the unitary operator which tells me how the system is changing in the first place. So finding Hamiltonian is also very important. Okay, finding Hamiltonian is also important. Knowing the Hamiltonian, you can know the unitary operator. Okay, that's a very important thing for the sensing. What is important thing for the sensing? Important factors for sensing is, okay, Rajesh class. Important factors for sensing is to find the Hamiltonian and then find the unitary operator which is having the Hamiltonian inside as an information. Okay, so in the quantum system, I need to know what is the Hamiltonian of the system and the surrounding together, and I can find the unitary operator which tells the fate of the system. Okay, so that is the basic foundation I would be needing to do the sensing of a system or sensing of the surrounding using the system. Okay, right? So that is motivation. In the later part of the session, I will talk about what is theoretically sensing could be in the quantum case. Okay, and how do we go about all those things we'll discuss. Okay, so I'll just quick break. We'll take here for 5 minutes and then we'll restart. Beta, not alpha. Okay, so there is some mistake I made. Where did I do? No. Which place? Which place? Okay. Okay. There is a small mistake here. I mean, this is not there. Okay. Okay, let me write down cleanly. This is E1. Okay. Okay, let's remove this. Okay, E1 dt. Okay, divided by IH cross. So let me write E1 here. Yeah. So I think it's fine. There is somewhere I had put beta in place of alpha. No, I guess. What I mean here, come on, here. Similarly, what I mean is similarly, we can obtain, okay, we can obtain this equation. Okay, right, Gauri ji, I don't understand. Have I missed some alpha, beta, some places? Let me check. No, I guess. Anyway, you can. Ah, how could we calculate momentum of a particle at all time if a motion is not unique? Ah, okay. So good question. Yeah, we cannot calculate momentum of particle all time. That is what Heisenberg uncertainty principle is saying. It's not Heisenberg uncertainty principle is saying. That is what nature actually inducing that kind of a constraint. What I mean is, if you go to a smaller and at quantum level, okay, means very small level where things cannot be certainly said to be a material or a particle. In that case, particles do show some kind of a wave kind of a behavior. They are not a waves, they will not become a waves, but they show some kind of a wave behavior. What I mean is, if I just take a small electron, it is not going to exist there, it is going to exist everywhere in the location. Let's say I have a small one dimensional box, it goes everywhere. So something which goes everywhere is like a wave. So if I have a wave which is distributed, okay, I would find the wave location everywhere, wave located everywhere. So the electron is behaving like a wave. So in that case, the electron position you can find by just taking the absolute square of the wave function. Okay, so if you find absolute square of a wave function, wherever there is a peak, that peak location would give me the maximum position of the electron. Wherever there is a no peak, means wherever it is a thrust, the strength of the wave is low. In that case, electron presence is absolutely zero. Okay, so it is a probabilistic in nature. So people say electron shows a wavelength of h by mv, Planck's constant divided by mass into velocity, where mass and velocity multiplied gives a linear momentum. So mass, size of the particle is important, velocity of the particle is important. If you don't have a smallest particle, if you don't have a velocity close to the light, you will not able to see this kind of a wave nature. Okay, when things are so small, in that case what happens, I can't specifically calculate the momentum or a velocity explicitly. Means there is always I'm going to make a mistake in finding its momentum. Some small delta p amount of error I will make. So, and also at the same time, I would also make a small delta x of error in finding its position. So, the product of these two would always be greater than Planck's constant divided by some 2 h cross by 2 or h by 4 pi. So, this is Heisenberg uncertainty principle. Okay, right? So we can never able to find a position and momentum with exact values. So, answer to your question, Dr. Surendra or somebody, how could we calculate momentum of a particle at all time if the motion is not unique? So here, of course, we cannot find for all time. Okay, right? So there is a uncertainty is also there even in time also. What I mean is, if you try to find the energy of the particle, so that also you would make a mistake by this way. So the error in the energy, okay, you will take some time period. Within the time period, you are going to find the energy that is also going to have some small error. So this is another way of seeing things are not fixed in quantum domain. Okay, right? Okay. So we'll take a couple of minutes and then get back. Already 3 minutes passed. I hope I answered your question, Surendra ji. Okay, so we can start, right? So just to see the what we have started with. So we started with understanding what is the sensing in the first place. Okay, we took some simple electric field or magnetostatic examples, how this testing or sensing is done. Okay, the same fashion we want to do in our quantum domain or a quantum hardware case. So there, the qubits are the entities which we are actually working with. So we should know how to sense them, how they are going to get affected by the surrounding, means how these people are sensitive to the surrounding also we want to know. So as we know, they undergo the change in terms of their probability amplitudes evolve in time. So which is represented in terms of some evolution matrix which connects their probability amplitudes of old ones to the new ones. Okay, so in fact that unitary sorry in fact the unitary operator is consisting of the energy of the system, that is Hamiltonian of the system. Okay, so knowing the surrounding energy and system energy is also very important in constructing that unitary operator. Okay, so now what we'll do, we'll go ahead and try to understand little bit more on the quantum sensing in some scientific manner. Okay, so let's say I want to define a quantum sensing in a theoretical manner. Okay, So I would say definition wise, quantum sensing definition. Okay. I'll not give a theoretical definition. I'll just give a, like, so points by point you will understand. Okay. So for sure, it uses a quantum system. Number one, it uses quantum systems. Okay. Right. And how it like it uses that and uses their properties. Okay. And like these properties are going to change, or the system and its properties going to, okay, let me write down a separate line. Uses, okay, they undergo change. Okay, so we will the change as a phenomena. Okay, right, when it undergoes a phenomena. Why? Because of external environment. Okay, which could be in terms of fields, either magnetic field or electric field. Okay, so quantum sensing uses systems and their properties which undergo a change as a phenomena because of the external means or external environment. Okay, so there the entire thing could be a physical phenomena, or it may lead to some physical quantity, okay, which could be measured. Okay, we can measure that, right? So this way the quantum sensing happens. Here in this case example would be qubit. Okay, so remember, let me give one historical information. Okay, even before quantum computing came, right, even before that, people were started using like this kind of a quantum sensors. Okay, right, so they're actually called historical examples. Okay, historical examples, if you want, let me give those things. One is magnetometers. Okay, what they are based on? They are based on semiconductor quantum interference devices. Okay, based on semiconductor, okay, quantum interference devices. Okay, right, so that is one. And one more is our simple atoms. They're very sensitive to the external field. So you can take a collection of many atoms, they're going to become an atomic vapor. So that is could be a very good means to sense the field strength. And also people use something called atomic clocks. Okay, atomic clocks are also very good sensors. Basically, they sense the external field strength or something. Okay, so this is a historical examples where people started using quantum systems to measure the field strength or measure the signal strength. Okay, right, so recently, okay, so the sensing, quantum sensing is actually growing its dominance in the field of quantum science and technology. Okay, quantum sensing is being perceived a lot due to its its high precision, very high precision. Okay, in fact, that precision is not possible in the case of classical system, classical sensors. Okay, right, so the most common sensing platforms. Okay, right, okay, most common is the spin qubits, spin qubits, right? Another one is trapped ions as a qubits, trapped ion qubits. Number three is there is something called magnetic field based, they're called flux qubits. Okay, so they're all quantum qubits, you see, right? So what is flux qubit is, so they're actually superconducting based qubits. Huh? Okay, they're actually superconducting, okay, superconducting qubits. And also we can have charge based qubit. Okay, you can use superconducting along with some capacitor. You are going to create something called transmon qubits. Okay, right? So that is the three major platforms where people use to create some sensors. Okay, so just for your clarity, what a flux qubits is, flux qubits are like some kind of a loop. Okay, some kind of a superconducting loop is there. In the superconducting loop, there is Josephson junction arranged in all the four walls. Okay, so let me write Josephson junction, Josephson junction, Josephson junction, Josephson junction. What I mean by Josephson junction is, okay, I just take a superconductor, not a semiconductor, superconductor, and I'll take an insulator, and then I'll take a superconductor. Okay, so this is called superconducting, insulating, superconducting. Okay, a sandwich. Okay, now superconducting, when I cool to millikelvin cooling, what happens is there are electrons which pairs up. Those electrons hops between one side of a superconductor to other side of a superconductor. Okay, and create some kind of a oscillating effect. Because of this oscillating effect, okay, so I could create some kind of a current going through the loop, either this way or a clock way or an anti-clock. So both of them I can represent them as state 0 and state 1. How? I am going to induce some magnetic field strength on this loop. I am going to create a positive, sorry, so clockwise or anti-clockwise current flow. So that is not fixed. It is sometimes this way or sometimes that way. So it's like a state of superposition. Okay. So here some Dr. Padmavati ji is pointing out, yes, superconducting, it is not semiconducting, squid. Yes, yes, you're right. Okay, so superconductor, semiconductor was there in back earlier in magnetometers, not at this point. In the quantum sensing case, yes, it's a superconducting. In the old and like very earlier, people were using semiconductor quantum interference devices. Okay, right? Fine. So now let's go further. Okay, so a perfect current flow is very, very important to have, which is only ensured with the magnetic flux. And whether it is forward or a backward, how much time is forward, how much time backward, it is like a qubit being in ground and excited. Okay, fine. Now, right? So these three things, if you take like whether it's take a flux qubits, magnetic flux qubits, or a trapped ion qubits, or a spin qubits. Okay, you take any one of them, so they are going to be seriously sensitive to the external surroundings. Okay, so we could exploit this thing. Okay, what we can do, we could exploit the sensitivity of this system to realize a quantum sensing effect. Okay, so how do we do is they are known for very fragility for the external means. That is one thing. Number one, highly fragile. That is usually it is as a, taken as some kind of a disadvantage, but we can use that fragility to measure even a very minute external magnetic field or a electric field. Okay, right? So even before the birth of computers, this above quantum systems being used for realizing applications like a sensing. One of the example I will tell you, it is actually called light meters. Okay, as you can see in the cricket at the evening when the test match is going on, umpires comes up with the light meter. Okay, basically it is actually made up of selenium photocells. Okay, they respond to the external electric field, sorry, light. So which was 1931, it was being invented by Winston. Okay, fine. So since they are so fragile to the external light, there will be some change. How much change we will measure? Okay. So even it is possible to capitalize the sensing. Okay. So for finding the external field and electric field, not only light. Okay. So what we can do is we can sense whether even the varying magnetic field or varying electric field also we can sense. If I'm talking about electromagnetic field, the electromagnetic fields, okay, basically it is a light. Okay, we can sense how much light is coming. Okay, what we do, we will sense with respect to frequency, mu. Okay, right? And we can sense with respect to the surrounding temperature. We can sense, okay, we can sense temperature around. Okay, we can sense pressure around. Basically, all these things going to influence the nature of the quantum system. They undergoes a change that is we can explain and understand. Okay, right? So now let's describe a quantum sensing in a nutshell. Okay, right? Quantum sensing in a nutshell. Okay, I'm going to fix once for all what is quantum sensing. Okay, it describes a method of involving a quantum objects. It involves, number one, involves quantum objects. Okay, for example, superconducting qubits or the spin qubits or neutral atoms also you can create a qubit. A trapped atoms I can create a qubits. So these things could be used to involve and measure the external physical quantity. Okay, fine. So, which could be classical or a quantum, doesn't matter. Remember, classical or quantum, both cases is possible. Okay, classical means you can take too many things together. You can make it a macroscopic system sensor. If it is a quantum, I'll take a very few quantum systems. So I'm only talking at the very small atomic level or a quantum level. Okay, so it describes even the use of quantum coherence. Okay, what is the quantum coherence is? As you can see, quantum qubits, okay, they're existing on a coherence means their superposition is going to exist, oscillation is going to exist for some time. Okay, for example, if I plot the oscillation between 0 and 1 with respect to time, I'll have a nice oscillation in time. After some time it is going to decay. Okay, so up to some time I have a very good oscillation that is actually called the superposition coherence time. Okay, beyond that time it is not. So you can represent that with some coherence. Ground to excited, it stays there in the excited state for 1 microsecond. That is required on an average. If it decays even before that, or if it without staying for 1 microsecond, it decays with some decay rate which is equal to 1 over T1. Okay, so where T1 is the time which is less than 1 microsecond on an average, in that case, again, I will lose the requirement of the quantum system to behave like a quantum in the first place. So there is a loss of coherence can happen even in the superposition state, or even it can lose in a change, like a chance of creating a superposition state in the first place. Okay, so right, so like the quantum sensing in a nutshell describes even the use of quantum coherence, okay, to measure physical quantity. Okay, why? Because the T1, T2 would be influenced by the external surrounding. That is what we want to measure in the first place. If T1 is some fixed value of T1, T2 will be there in general. Those things are changing means they're actually changing because of the environment is going to interact. Okay, so that is number two. And number three, okay, so people even started using the quantum entanglement. One of the profound effect of quantum systems is quantum entanglement could be used, okay, not for just for the sake of using, you can use to enhance, okay, the sensitivity. That is possible, by the way. So you got the moment you bring in the sensitivity, enhance the entanglement, you can even measure much smaller magnetic field or electric field strengths, which were not even possible with the classical strengths, classical sensors. Okay, so this is what the quantum sensors in the nutshell. What I mean is, if there is any sensor which would exist, which will fall under the level 1 and level 2. Okay, so 1 and 2 more or less covers all the quantum sensors, right? 1 and 2 cover all existing sensors, especially quantum. Okay, right? So if there is something like exceptional case use where quantum entanglement is used, where entanglement is created, entanglement is used to enhance the sensing, means there is a qubit which is entangled, goes near to the signal and gets changed, and whatever that change is happening in that qubit, its entangled pair would undergo. So that change in the one which is not in the vicinity, right, to the signal, like it's a very good a remote kind of a sensing. Okay, right? Yeah. Yes, people were saying there is a light meters being used at the movie shootings, yeah, to figure out how much light is there. Yes, the sensing is not necessarily meant to moving states. Then what about sensing a static state? Okay, right? So see, for example, what I mean by sensing in our case is our quantum states. If you just take, okay, in a Dirac notation, I'm writing. If you see, okay, this is a Dirac notation, by the way, a quantum qubit state. So here, probability amplitude alpha t beta t are time dependent. Why they are time dependent? Because the system is interacting with the surrounding. So alpha and beta actually evolve in time. The probability amplitudes are evolving in time. So which means the quantum state is going to evolve in time. It is not moving, it is evolving in time. So maybe there is a motion, there may be a quantum qubit goes here and there, but I can't say it is moving fixed way, right? Because it's a quantum in nature. But what I can certainly say about its quantum ground state energy and excited state energy. Okay, alpha in terms of alpha t and beta t. Okay, right? Fine. So, right. Okay. So, what is this quantum qubit being? Okay, time dependent quantum state. Okay, right. Now, yeah. Now, what we'll do is next we'll go. Okay, let's say I have a qubit I am going to use for sensing. Okay. Now the question is any qubit can be used as a sensor? That's a question we should ask, right? Okay. So, okay. So there are some conditions, or we can say there are some necessary criteria, okay, for a given quantum system to become a sensor. Okay, very important, right? If you just recollect, to create, to compute, to do the quantum computing, there are some criterion which were set by the gentleman called DeVincenzo. DeVincenzo. Okay, DeVincenzo criterion. Okay, so he has set a criteria that quantum system has to be created in a certain fashion. It should allow for interaction. It should evolve in time. All those things are there. Just we will take a page from there and we'll define some conditions for a quantum systems to become a sensor. Number one is the quantum system should have discrete states. Must. Discrete state is must. Okay, what I mean is there is a ground state, there is a excited state separated by some energy gap. E is equal to some h omega t. So that is very much important. Okay, right? And number two, we should be able to initialize the system, initialize the system to a known, remember, to a known states, not unknown states. So the known states here is 0 and 1. We should be able to initialize the system into these known states. Okay. And number 3 is, okay, and the system should allow, right, to manipulate the system. It should allow the surrounding, should allow the surrounding or the environment to manipulate. Okay, remember in a coherent fashion. Okay, I'll put coherently. Okay, and here the coherent manner means there could be electric fields which could be time dependent or time independent. Okay, so when I say time dependent, I'll have a time dependent interaction fields are involved. Otherwise, continuous wave spectroscopy we could use. Okay, number 4, the criterion for a quantum systems to become a quantum sensor. Number 4 is they should allow, very very important, this quantum system should allow the external interaction, not only manipulate. Okay, they should allow to a good extent, not to a greater extent, external interactions. Allow external interactions from physical quantities, various physical quantities, which we need to measure. Okay, right? Only those things. Remember, not everything, only the quantities which we will need to measure. Let's say V of t, where V could be electric field or magnetic field. Okay. So how exactly it is going to induce is the V external magnetic field or electric field is going to create, there is a change, you see, there is an electric field, sorry, there is the separation between ground excited state is there, energy gap is there, no? That is going to change, is going to change with respect to external field magnetic field strength or electric field strength. Okay, so that I will write as derivative with respect to applied field strength. So remember, so this is actually called a kind of a coupling parameter, or it is also called a transduction parameter. Okay, we'll say simply coupling parameter. Okay, so this coupling parameter sometimes is actually single derivative, sometimes it is a higher order derivative, which means when q is equal to 1, linear dependence, which is actually refers to a linear variation, and anything, let's say 2, it's a quadratic variation. Okay, response is quadratic or non-linear. Okay, so both are possible, by the way. Fine. So one scenario would be, if I just take a quantum system to exist in the excited state, when it is excited for 1 microsecond, even before that it just decays because of external environment. Okay, in this case, what should I do? My external field strength should coherently match with this coherence, this decay rate time. Okay, right? So that is the condition. Fine. So these are the four criterion points a quantum system should satisfy to become a sensor. Okay. Otherwise, if some condition among this is not satisfied, then we might not able to measure perfectly the external parameters. Okay. Now we know what is a quantum sensing. Okay, what are the things we need to keep in mind? So to make a quantum sensor, what are the criterion also we need to keep in mind? Those things we just saw. Now, yeah, now, we are going to that. I think Surendraji was asking, can you please mention some quantum sensing objects, so that we can understand easily? Of course, that is what we are trying to do. We are trying to see some types of sensor, some classification. Okay, so classification of quantum sensors. Okay, earlier we just I gave a simple examples, some sensors. Where did I give some sensors? Here, a spin atomic vapor people are using, atomic clocks people are using for sensing, spin qubits for people are using, trapped ions people are using, and flux qubits people are using. These are all sensors for us now. Okay, right? So for a minute, like just for the sake of answering the question, okay, there is something called NV centers. NV centers in diamond. Okay, that is the one of the leading magnet in the biomedical application, being used to sense the magnetic field or the electric field strength given by or created by human tissue or any tissue, a biological tissue in the first place. Okay, so what they do is they take a diamond. Okay, diamond is made up of carbons, right? Carbons. Okay, remove a couple of carbons. Okay, you create a vacant space of carbons inside. In one place of a carbon, you put a nitrogen by doping. In another place, you leave it as it is. When you put a nitrogen inside, it creates a negative charge. When I remove a carbon, it becomes a positive charge. Basically, it becomes a negative and positive charge separated. It creates a dipole. Okay, NV center, they call NV center dipole. This dipole is very, very sensitive to the external electric field and also the magnetic field. So, how much magnetic field strength is around this? So, they create some kind of a probe. Okay, a probe is created. At the tip, they place this NV center based tip, and the magnetic field is there, electric field is there. Let's say there is some positive charge is there, that is going to influence this. How it is going to influence? It is going to change the band structure or some kind of a electronic structure of this NV center, which is basically just like two level atomic system, like 0 and 1. If there is a magnetic field around or electric field around, what happens is the ground state splits and excited state also splits into two parts, two states. Now, the number of electrons, if there are so many such NV centers, the electrons, some of them will here, okay, some of them are here. Many of them, let's say here, then if I supply a photon having energy separation equivalent to this field, this levels, the lower level and the top level, only in that case electron would jump, otherwise they will not jump. Okay, if the electrons are here, this we will match with this, the input photons. Okay, so input photons would push the electrons to the excited state, means they will, what they do, they incident a light with a red, a green color light is incident, and if there is a some pink color is reflected, which means there is a spectrum, there is a split of the ground state and excited happened, means external magnetic field is there. If the same green color comes out as it is, so there is no magnetic field. So this is how they are going to find the external magnetic field. Okay, okay, so this is NV center based sensor. We'll get into the details later on. Okay, so right now what we do, we try to understand what is the classification of different kinds of sensors. Okay, right? So as we can see, the sensing can like sense either charge, external charge, or a magnetic field as an electric field. So electric field or magnetic field. Okay, okay, so they're like spin based. That means we can divide the sensors into two things. One is electric field sensors, another one is magnetic field sensors. Okay, right? So some sensors, for both they will respond. Okay, and there are sensors which responds to the temperature, and there are sensors which responds to the external pressure. Okay, right? So we can keep going dividing the sensors. Okay, and a better sensor would be the one which only responds to the required signal to be detected. It should not detect anything noise. It should only detect the required signal. So that is a better sensor for us. Okay, and they should have a very good sensitivity. So a sensitivity you can use, okay, you can use to define a kind of a sensor. It's a very good sensor with the sensitivity, or some sensors with the sensitivity compromised. Okay, so basically sensitivity is directly not directly proportional, indirectly proportional to the coupling factor gamma, which we saw earlier. Okay, this is a right, and it also indirectly proportional to the square root of, there is something called the coherence time of the sensor. Okay, so coherence time, you can remember, I want system to behave as per my wish for some time, but it is losing its nature even before that. So that is what I'm losing the coherence time there. It is decoherence. Okay, or you can say T of x would tell me the immunity time of the sensor. So it is immune for the surroundings or unnoise for some time, and after that it will be compromised. So I have to ensure that my sensing is done within that time, because it might induce some unwanted decay of the system here I was showing. Okay, right? Fine. Now let's go further. Okay, we have another 10 minutes. Okay, so now let's see the quantum sensing methodology. Okay, quantum sensing methodology. We have so far understood what is the sensors, what is the quantum sensors, and what quantum systems can become a sensors. Okay, and how sensors are classified. Now let's say I have to use a sensor. Okay, what is the methodology I should follow to do the sensing? Okay, if I have to divide into some certain number of steps, I will divide into 3 steps. Okay, number one is initialize the quantum system, or initialization, okay, of a quantum system, which is I'm going to use as a sensor. Okay, number two, interact the system, okay, with a signal of interest. Okay, interact with the signal of our interest, not unknown unwanted signal. You remember, only interested, like I want to find the electric field around, but not the temperature around, not the magnetic field around. Okay, right? Then once the interaction is done, I should be able to read out of the final state. I have already initialized now. After initialization, it has gone to some other form. I have to read out the final state of the sensor. Okay, so this is 3 steps I should be using for a methodology. Okay, so basically this quantum state of a system goes change from one form to other form, that I will going to pick up and going to understand. Okay, so what it that could be, for example, the quantum state is like this. Okay, for example, it undergoes some change, it picks up some phase. What is that phase? Some relative phase it picks up. What is that relative phase? I put a minus sign in place of in front of beta, which is that it is adding a phase term of exponential I pi for only one ket. What is that quantum state would be? The gate would be this gate. What is this gate? This is a Z gate. Okay, so quantum state picking up a phase would be one way of sensing the external effect. Relative phase is being added here. Okay, so there are so many gates we have seen so far. There is all sorts of gates could be used to understand what could be the effect of the surrounding. Okay, right? So in the NV center diamond case, okay, I just showed you earlier. Okay, so there is a sensing tip is there. Let's say this sense a pump field of green color. and let's say there is a pink color coming out along with the green color. Okay, if pink is there, that means the external magnetic field is around. Okay, if pink is not there, means no magnetic field. Okay, right? No magnetic field, no pink. Magnetic field around, yes, pink color, reflected light. Okay, so this is how people use a sequence of pulses or the laser pulses to recognize the surrounding magnetic field strength along with the probe they use. Okay, right? Now, let's say I want to explain this, how the sensing is happening. Okay, mathematically, let's say I want to explain. Okay, so what I do, I can use some mathematical, because all the way we use mathematical equation to describe a quantum system. So a mathematical description would be a very good option to understand how the sensing works in the first place. Okay, as we have seen earlier, a quantum system being undergoing a change because of the environment means its corresponding energy is going to change. Energy is going to change means its Hamiltonian is going to change. Okay, so let's say it is initially some Hamiltonian is there, internal Hamiltonian, which is like internal Hamiltonian initially like this. Okay, which interacts. Okay, let me explicitly write down what is this, zero, outer zero. Okay, let me cleanly write zero, outer zero, E1, outer 1, outer product. Here I am writing. Okay, all right. Now internal Hamiltonian, I know. Not only that, it is being exposed to the surrounding. So I will write there is a external field Hamiltonian. Okay. Let's say if it is time dependent electric field and a magnetic field is there, Hamiltonian also becomes a time dependent. Okay. Now I sometimes I want to keep the system in control. I don't want this quantum setup or a sensor which I have taken to completely exposed. I want to only partially exposed. So I want to have a control. I'll induce the control through some control Hamiltonian. A mathematical model involves a Hamiltonian to describe the quantum state energy or the quantum system energy of the sensor would have a Hamiltonian like this. Okay, right? Now, because of the environment, there will be coherence, decoherence. All those things were actually captured inside the second term HV. Okay, right? So even we will call HV as a signal Hamiltonian. Okay, right? By the way, it is time dependent. Fine. Now the signal Hamiltonian might come and play with a quantum system. Okay, it might induce some change. So that change could happen in multiple ways. Okay, what is that change is, I can have multiple ways of interaction, but what I'll do, I just only define in only two ways. Okay, what I mean is, let's say let's say a classical world, let's say I have a pendulum which is steady. Okay, what I do, I create an amplitude and shift the pendulum, okay, to some deviation from its steady state, and it can create an oscillation. So I have disturbed the system from its steady state, and the disturbance is creating a oscillation. So in terms of physics, people call it as perturbation. Okay, so it's called perturbing or disturbing the system from its steady state, perturbing the steady state. Okay, so here I am creating an amplitude. The here HV is perturbing the the system or a sensor which is steady. Okay, which is in a steady state, by the way, but I am disturbing it. Now, how I am disturbing? Again, I can disturb in sync with the applied field or in opposite with the applied field. They call it as the HV can have either effect in sync, okay, and also sometimes it is not in sync, it is called opposite, or you can say perpendicular to the applied field. Okay, right? So it's like you say you push something moving in the same direction, but interestingly, if you push something moves to the perpendicular direction, okay, right, some kind of a hall effect or some kind of thing. So because of that kind of a effect, you can divide your interaction Hamiltonian or signal Hamiltonian into two parts. One is the change it induces in sync or in the direction of its applied field in the quantum sensing. So that is one. Other one is perpendicular to that. Okay. So literally, if I have to write down what would be the parallel component of the signal Hamiltonian, which could be, we will use that coupling parameter to define, which is V parallel time dependent. Okay, there is a one outer minus zero outer product. Okay, so this is a parallel component. Okay, very good. Now, what would be the perpendicular component? Which is half coupling parameter. I'll put the flower bracket now itself. V perpendicular component, one outer product with a zero, V perpendicular dagger. Okay, it's a complex, it could be a complex, it could be a matrix. So I'll have zero outer with one. So this is what the perpendicular transverse component, they say, transverse component. Okay, transverse to the qubit, if we can say, transverse to qubit, parallel to the qubit, its effect. Okay, now the gamma which we are earlier writing, the coupling parameter, which could be, if it is we are we are measuring some kind of a electric field strength, okay, right, some kind of a electric field strength. In that case, there is electric ground and excited states are there. They're going to create some splits. How much split is going to happen? Let's say some change in the earlier, this is the separation. Now let's say separation got changed. How much separation got changed? Let's say it's changed with some h per applied magnetic field strength. Okay, this would be a Zeeman shift. Okay, remember, same kind of a shift also can happen with the electric field strength, H versus volt per meter. Okay, so this is actually called, okay, linear Stark shift, or you can simply say Stark shift. Remember, it happens in a linear fashion. That's why it's a linear Stark shift. Okay, so we just defined what is the mathematical form of the Hamiltonian having two parts. Now the third part is control Hamiltonian. Okay, so third part is control Hamiltonian. What we do, we'll just discuss that control Hamiltonian and how this interaction Hamiltonian HV, mathematically you can write down explicitly, right? Here I have only written the perpendicular and parallel component. In the next session, that is tomorrow, we'll discuss little bit in detail what is HV perpendicular and HV parallel, also what is H control. Okay, right? So that is we will see tomorrow. I'll stop at this point. If there is any questions, I'll ask. So before going there, let me summarize quickly. Okay, in the second of the session, where did we start? Second of the session. Okay. Okay, there was a question somebody asked. I think that is the point. Yeah, uncertainty principle, right? Okay. So we start in the second of the session. We literally started defining explicitly what is a quantum sensing. So where a quantum sensing is nothing but quantum system and its properties going some change because of the external parameters or a physical quantity, which we will depend change in the physical properties will take into consideration and will measure physical quantities around. There are historical examples people started using even before computers coming in, using semiconductor based quantum interference devices or atomic vapor, even light meters. Okay. Later on, quantum computing picked up, quantum hardware picked up. For the sensing, people started using spin qubits, trapped ions, flux qubits. We explicitly saw what is a flux qubits are. How are we doing sensing? We are exploiting the sensitivity of these quantum systems as they are highly fragile. Okay, they may respond to electromagnetic fields, right? And they respond to the temperature around and pressure around, and we can use that to sense. Okay, quantum sensing in a nutshell would involve very basic 3 points. One is they measure external physical quantity. It could be classical or quantum. They use quantum coherence to measure physical quantity. We saw what is a quantum coherence. And we can use quantum entanglement to measure high precision sensing effects. Okay. So basically, whether we use the first method or second method, which will cover all existing sensors. Okay, right? So just like Davis-Injo criteria for quantum systems to allow us to do quantum computing, similarly, quantum system to become a sensor should satisfy some properties. One is they should be having a discrete states, should be able to initialize into known states, should allow surrounding to interact with them. It should only interact with the like a signal but noise, not the noise. Okay, and we can divide the sensors into categories by charge sensors, field sensor, temperature or pressure sensors, where the coupling parameter and the coherence type is going to play how much sensitivity we can arrive with. Okay, right? So the methodology of the quantum sensing involves 3 steps: initialization of the system, interaction of the system with the surrounding, reading out the system. So basically, it's like inducing some phase change, for example. Okay, so if I have to see how the quantum system undergo change, okay, that change is used to do the sensing. So if I have to mathematically describe that, I do the mathematical model starting with the Hamiltonian of the system involving 3 parts. One is the internal Hamiltonian, that is a sensor Hamiltonian itself, okay, and signal Hamiltonian, and I have to control the interaction between them, okay, that I use as a HV control. Okay, right? Yeah, there was a question asked by Dr. Padmavati ji. Okay, I'll come back to that. So we explicitly saw what could be the interactions Hamiltonian would look like. Basically, it can induce change in parallel or in perpendicular to its direction. So in that case, what it would look like, we just saw. Okay, we will see what is a control one and what is the interaction Hamiltonian. Okay, in detail tomorrow. And let's get back some one question here. Quantum state change due to pressure in sensing applications. Okay, right? So a very good question actually. When I say a quantum qubit going under some change, I'm not going to take a one single qubit. I'm going to take a collection of qubits, many qubits though, right? So if they're reasonably placed away from each other, probably they may not interact much, okay, and there will not be a much change in their state if they are not interacting much. Let's say the pressure is high, means they were put under so much pressure, they haphazardly move, they interact with each other, they globally change themselves. Overall, how much change is there because of the compression, like a pressure increase? In that case, I see some change in the system. So basically, let's say I have taken a system or qubits, let's say some 100 qubits, all behave like a quantum state psi, which is alpha 0 plus beta 1. All of them. But later on, because of the pressure, what happens? Let's say pressure is there from all the corners. Okay, because of what happens, the corner ones comes in and interacts and hits the ones inside. So let's say the corner ones are going to change to quantum state psi, inside ones are existing in, let's say, quantum state 2. Okay, and inside one, let's say again there is some division, let's say some quantum state psi 3 also exists, psi 4 also exists, and so on. Let's say some psi n quantum states. What I mean is, if I just take a like atoms, like qubits, because of the interaction or because of the pressure, they're going to become a different quantum systems. So now I can't represent them all of them in one way. So I have to bring in, there is something called a density matrix. So density matrix would address how many qubits are there in the psi 1 state. Okay, so basically density matrix is nothing but outer product of quantum state with itself. Now, so there are groups of atoms. Let's say the entire group becomes into parts like psi 1, psi 2, psi 3, okay, and psi 4, okay, right? So there are groups become, so I'll write overall quantum state density matrix as rho total. There is a quantum systems in rho 1, there is a quantum system in rho 2, and so on, rho n, okay, right? P1 stands for the probability. So rho 1 means psi 1 outer psi 1. So basically, let's say how many groups I've created. Depending on that, I can find the pressure. Okay, a quantum state becoming a density matrix or a mixed state from pure form. So here initially it is a pure, becoming a mixed state, having so many induced groups, would could be used to measure the pressure. Okay, or even temperature. Fine. Fine. So that is what I have come up with this kind of an explanation. So there may be some other explanation. If you can find, let me know. I'll have that. Okay. Thank you. So we'll stop at this point. Let's get back tomorrow. So I will be uploading this my running hand notes as well as my lecture notes explaining all these things in detail. Probably some motivation which I have brought in here, the charge description to measure the external magnetic field, electric field and magnetic field. That may not be there. Straight away, it will start with the quantum sensing also. So if needed, you can use that to have some motivation and understand. Okay, right? Okay, fine then. I will stop at this point and I'll hand it over to our host. Okay.
Thank you so much, sir. It was I couldn't attend the full session, but I can sense it was a wonderful session, and the participants are requested to utilize the notes as well as the lecture slides which will be provided. Apart from that, we also have this particular AI assistance in the WebEx. So, in case if in between if you are going away, once you come back, you can utilize it to understand what was discuss when you were away, right? So I request all of you to use AI assistance along with WebEx, which is available. Anil sir, do you want to add anything? Okay. So then we'll continue tomorrow. Thank you so much, Aswat sir, once again.
Thank you, Mahibal sir. See you tomorrow.
Okay, thank you.
Okay, bye
Okay,
bye.
okay. Bye.